And thanks for the organizer invitations. Today, I'm Meng from UCLA. Today, I'm pleasure to share with you about my recent progress about the conjugated molecule materials. For the pet molecules materials, it always maybe like the organic molecules that be connected with the carbon atoms or the hydrogen atoms by the sp2 or sp bondings to form the localized the orbitals. The synthesized reactions and maybe the aromatic properties of the pet molecules, maybe it helps the one maybe is the occurs content of the chemical senses. Maybe as another important thing is maybe the paired-conjugated molecules, it can easier to synthesize and its properties and the structures can to modify through the molecules, the tailoring, the molecules designs, and the molecules assembly to realize the maybe the virus, the device, the applications, such as maybe the OFAT, just maybe it's the organic solid cells, maybe it's like displaced and the lives, process, maybe it's the transistors and the carbon dioxide reductions. Maybe so research mainly focus on the paired-conjugated molecule materials where I want to maybe develop the different molecule structures and systems, and maybe it's the realize the different assembly structures to achieve maybe the techniques innovations and maybe it's breakthrough the performance. Before we do the paired-conjugated molecules, we first must to understand the original design principles. Maybe from the first one, we must to select maybe the better molecule systems. Maybe it helps the better conjugate configurations, so we can to modify the molecular structure and then to achieve the different assembly structures, and then maybe the different assembly structure it can achieve the different physical or chemical properties such as the maybe absorptions and the levels and the differences, maybe the morphologies such as the different shapes about the crystals, and to match the different applications such as OFAT, OLED, or the other applications. But each process maybe it has to feedback to another process. It can form maybe beautiful feedback systems. We can maybe also use the maybe simulations methods to get the better understanding for the help to design the molecules and achieve the different assembly structures. Before we also understanding the principle, design principles, we must know the roadmaps, and we must know where is the question and how to match the questions. For the paired-conjugated molecules materials, we must understand the two major questions. The first one is how to accurately synthesize the paired-conjugated molecules. Another one maybe also precise the controls the aggregation structure of the paired molecules, conjugated molecules. So after then, we must to select maybe the research systems. As the conjugation systems must with the multi-dimensional topological structures, and then we must select maybe the better molecule systems, such as maybe we realize those multifunctional organic paired-conjugated materials. So this is my outline today. My two major research progress. First one, the high performance acceptor materials for the organic solar cells. We choose the paraimized as the research items. As another one, we also use to develop the supermolecules, the organic porous crossing materials. We also use maybe the spiral conjugate molecules. Assembly structures and the different applications. First one, for the organic solar cells, we must understand how it works, the principles. It helps to maybe 5 progress for the organic solar cells. For first one, maybe it includes maybe the photons absorptions and to maybe produce the excitons, and then to the exciton is to maybe the diffusions to the interface between the donor and acceptors, and then maybe to separate and to free charge, and then maybe to transfer the electrodes, and finally the free charge can do collected by at the electrodes. And this equation still about the PCE, it maybe also includes the main three items that maybe we call it the VOC and the GSE and the field factors. For the VOC from the materials to design, the VOC may be related to several items because the VOC may be determined by the energy level between the the donor materials the homo and the acceptor materials the lowmost, because the offset to maybe determine the VOC, and we want to make the VOC loss maybe is the as small as little. And last maybe is the interfacial contact between the active layer and the electrodes. And it is also maybe affected by the temperature and the films, the morphologies. For the GSE, it's mainly determined by the active layers, the materials, the absorption, because they have the absorption to have the absorb as more as the photons. And to get it must have the charge transfer efficiency, also better mobilities to get the highest current, and also related to films, the morphologies. For maybe the field factors, maybe it's the major two items for the equations. It also related to the charge transfer efficiencies, also better morphologies to get the better field factors. First, when we just our roadmap to send. First, we must to select the natural better the molecule systems, because the pairing amines it is the chemical structures. It has the 8 maybe reaction site. We can to modify it, because the pairing amines we maybe also call it the PDI. It has the highest mobilities, and it can to apply the difference in the organic electronics, such as the organic solar cell, OFET, and others fields. But we now mainly focus on the organic solar cells. But for this molecule systems, it's the main problems, because it has to maybe have larger the planar structures. It can easier to form the edge aggregations, and it can to form maybe the large domains. It can to form the uniform the network with the donor materials. So we must to control is the aggregation structures, must use maybe the twist strategies to avoid to form the edge aggregations. And then maybe we can to match the well with the donor materials, and to form uniform network, and to get the better film and get the better morphologies, and to improve the PCE. This is the several report strategies that includes maybe the single link and the fused links, and the different reactions, the reaction site. From the 2014, my main research focused on the pairing amines and applied organic solar cells. Firstly, we will use the single linked strategies to make the twisted configurations to avoid the actual interactions and to get the better morphologies. And then we also use maybe the hierarchical atoms the strategies to maybe get the better the twist structure, and get the better maybe the morphologies and the mobilities, because the sulfurs maybe has to have the maybe can add the more interactions between the intermolecules. And we can achieve the maybe 7% as 2015, but it is the highest PCE at that time. And maybe from 2016, we also realized that maybe the field student maybe have the all better mobility than the single links. But we also for the field stream maybe also have the maybe more aggregations than because these fields means they have the better the planars. So we must use maybe the stereo effects to make the fields range and twist. So we introduced the maybe such like the molecules we call it TPH. We can use the field range and twist structures to get the better mobilities than the single links, and we can also the almost PCE is also the highest the PCE at that times. And finally, we can also use the same strategies, maybe the field string and the twist structures, and achieve the approach to maybe the 12% now. And the research is ongoing. And for the details for the flexibles, the twistables, the heteroatoms, the strategies, we first use maybe the single links. It can twist structure. It can to avoid to form the H aggregations. And also we introduced the sulfur and the selenium to into the systems to get maybe the better morphologies and the better twist, because maybe this side confused and maybe the steric effect has the better to maybe get maybe the more twisted structures, more better morphologies with the donor materials can get the better morphology and the better maybe the mobilities. And then maybe the heteroatoms between maybe the sulfur and the selenium maybe have some more interactions and to increase maybe the better molecules, the peptide interactions, and improves the PCE. As then for the next strategies, we want to do detailed introductions, because we also use the rigid twist heteroatoms the strategies. We also use maybe the Suzuki interaction and maybe the photo light to make the fusion the rain fields to get maybe the compounds the TPH. And then we also introduce the seleniums to field strength systems to get the TPH SE. This is the crystals. From the crystals, it can to see its configuration look like the propellers. Maybe it can twist, but it's a fused. So it can to match the different requirement for the organic solar cells. This is the single crystal packing model. From that, it can to also to forms the 3D the stacking models and maybe the better interactions, because the from the selenium TPHSE, it can because it has the better interactions and maybe the shorter the molecule distance, because it helps the most selenium oxides the interactions and to make the molecules with the better and stacking and gets a better performance. Next one, because the apparently or the amines always maybe have the highest absorptions. When we added the more amines, we can get the better maybe the coefficient maybe it's better as the can to absorb the more sunlight. So we can introduce slacks maybe it's currently at the central curves to we can also introduce fives to paramized and to filter in the filter and maybe get the twist rigid and the twist structure to omit the organic solar cells. Also the reaction is also the same. But from the structure, we can see it has the helixes, the maybe structure is six helixes. But the helix structures, it has maybe have the different isomers because it has the different maybe the configurations, maybe the high and the different. This is the D5 symmetry configurations. It's like also the propeller, but not maybe the twist structures. We can to talk the details in the crystals. From the maybe each isomer, we have the two carriers in enantiomers. So we through the maybe it's the separation and then because the crystals to crystallizations to helps the two isomers. From the crystals we can see the D5s maybe they can help the propellers configurations, but the C2 symmetrics maybe the whole parent the unit and the up and the whole parent unit to the down. So but for the D5s the symmetrics we find that it has forms maybe 3 units to form the porous structures, and maybe the each layers and also forms the layer by layers assembly structures, and each layer has the pures to the enantiomers. It can form maybe the alternated to form the regular and the unit honeycomb the structures. It is very interesting. So it also maybe gives us a lot of curiosities to develop this, maybe it's the mobilities and other applications. For the C2 matrix, it can form the dimers, maybe through the peptide interactions, and it can form maybe the another maybe the rigorous assembly the structures. So because it can for the D5 the symmetric configurations, it can to form the unit and the interesting the honeycombs the assembly structure. So it is also maybe give us a lot of the curiosity to develop the its mobilities, because there it has no peptide interactions, but we want to know how about its mobilities. So we do the single crystals to transistors. This is the micro crystals, and we also do some characterizations to see the micro crystals maybe have the same lattice with the single crystals. So, and we also do the OFDT device, and we investigate the different orientations about the mobilities. We find it different orientations have the similar the mobilities. Maybe it has the isotropic properties. So it is this is the mobility to match the organic solar cells applications. So we also want to do develop the organic to solar cells to find from the two isomers. You find that the CRP1 has the better performance, and we also choose the P3TAA as the donor materials. It's developed by Professor Yan He from the Hong Kong University of Technology, and we can to know what's the difference. Why we can there's no peptide interactions. Why it also has the better morphologies. From the purest film, we find that the CRP1 as the CRP2, maybe the CRP2 has the better peptide interactions. Maybe it's matched with the crystal because it has the peptide interactions. But for the CRP1, maybe there's no peptide interactions. But when the maybe mixed with the donor materials, it finds that maybe it has the similar morphologies from the GVAX. But the difference between the AFM we find maybe it's the main case, because for the AFM we find that maybe the CRP1 maybe has the small domain size, maybe has the uniforms the morphologies in the CRP2, because the CRP2 maybe has the peptide interactions, maybe it have easier to aggregations, and it count to forms the uniforms the morphology with the donor materials. This is why maybe it has the better morphologies in the CRP1. So this is the for the solar cells part. We do a summaries for this part. We used maybe the just more adjustable molecules to configurations, and to get the precise regulation of the aggregations, maybe it's a different packing models, and maybe we can get the high performance acceptors materials for the organic solar cells. we can also invite it to write the review paper on the concept of the chemical research about the maybe the polyamides as the substrate materials for the organic solar cells. For the paired-conjugate molecules materials is another major research field related to maybe the organic porous crystalline materials. For the molecular porous materials, maybe it has to develop this more than years, maybe from the 1918s. There's different porous materials developed. So from the 1995, the Professor Omanyagi from UC Berkeley is to provide the more concept. And then last 10 years, he also developed this covalent organic frameworks. Now the two maybe have the better the famous porous materials in the field. And from the 2011, maybe another concept, the hydrogen bonded organic frameworks is provided, and it developed opens the different applications than the cough and the mouth. From 2020, we find we can use maybe the very weak the peptide interactions to can also form the permanent the organic frameworks. We call it the non-covalent pi-stack the organic frameworks. We call it as the PEF. We want to compare the three the other two famous porous materials. We find that the cough maybe always helps the porous to the conductivity because it contacted by the covalent band. But it's also the polymers, they count to solve the porous solubilities and account to make the device. For the MOF, because it can form the coordinate bonds, it has includes the metal, it has better maybe conductivities, but also it's the same problems. It counts to the solubilities and it counts to the device process abilities. But for our PEF, because it can form the non-covalent peptide interactions, also we can normally we know the organic semiconductors. Its transport channel is mainly focused on the peptide interactions. So because our system, the PEF, it has binding to peptide interactions. So I think maybe it has better the conductivities because it is the assembly structures. It is just a small molecules. It can easier to dissolve. So it has the good maybe stabilities and easier to develop the device processing. So this is maybe it has the better advanced than another famous porous materials. So we want to develop investigate the different applications. This is the synthesis route. We also select the spiral conjugations molecules. It has the 3D dimensional. So we also use the maybe IC groups as the end groups. It's also the major because the IC groups always have the peptide interactions. The face-on peptide interactions, it has better. So it can to use this one to as the link groups to form the 3D porous structures. It is the crystal structures. And from it is the assembly structure. It's just a single layers. From the structure, we can see so each molecules it can form the routines the 90 degrees to connect to another one. It can use maybe the peptide interaction to maybe it's distance about the 3.48 electrons. Maybe it's better the peptide interactions is the perfect face down the orientations. For the layers, the single layers, it can form the process about the 2.12 nanometers. This is the assembly models. This is the cross-links configurations and to forms maybe 3D, maybe the layer by layers structures. Because the two layers maybe have the slide. So it's a slight distance. Maybe it's 3.94 electrons. And making it because this is slight, maybe it's porous, maybe it's smaller. So maybe now it's the whole pore size. Maybe it's the 1.2 to form the 3D the structures, and finally it can to form the 3D the path structures. They're also invited to write the maybe says the our groups, and it also belong to their molecule systems to belong to the paths, the new class, maybe the new class the organic frameworks to belong to the paths our concept. This is another groups also confirms our concept. For the epoxy materials, we must do the solve the characterizations. We do the BET transistors. Maybe also do the DFT to get the final one to the whole transport layer. So why it helps better transistors? It is also use the characterizations to get the better applications. We also to use this method can to develop the OFET, OLED, and the other OP ways can differentiate the organic electronics. The summary we can get maybe it's a precise. Maybe we can use the precise synthesis and controllable the assembly of the organic p-conjugated molecules based on their functionalizations. Maybe we can to realize its application and improve its performance across the molecules fields. Maybe next one, maybe you can use the new design strategy to super molecules organic porous materials. Maybe the path, and maybe we want to achieve the new breakthroughs, new the functional and applications. Maybe use the new concept. Thanks for your attention, and this is my emails. Please contact me if for details discussion. Thanks for your attention.